According to the National Electrical Code, a ground fault interrupter protected main breaker is required for any service where the calculated available fault current exceeds 12,000 amps. In the provided scenario, the calculated available fault current is 3,000 amps multiplied by 13,800 volts divided by 240 volts, which equals 172,500 amps. This exceeds the 12,000 amps threshold, therefore requiring GFI protection. The ground fault interrupter protected main breaker must reference the neutral of the service to effectively detect ground faults. This means that the neutral conductor must be connected to the main breaker, and the GFI protection system must be able to sense any current imbalance between the phase conductors and the neutral conductor. This current imbalance is indicative of a ground fault condition. There are also some additional considerations. Firstly, the ground fault interrupter protected main breaker should be rated for the full load current of the service. In this case, the service is rated at 3,000 amps, so the main breaker should also have a rating of 3,000 amps. Secondly, the ground fault interrupter protection should be set to trip at 5 milliamperes or less. This is a critical setting to ensure that the GFI protection system responds quickly and effectively to any ground fault. Thirdly, the ground fault interrupter protected main breaker should be tested monthly to ensure proper operation. Regular testing is essential to verify that the GFI protection system is functioning correctly and will trip when needed. The purpose of ground fault interrupter protection is to mitigate the risk of electrical shock and reduce the severity of arc flash events. Ground faults can occur when current flows through an unintended path to ground, such as through a person or equipment. By detecting these ground faults and quickly interrupting the circuit, ground fault interrupters can prevent serious injuries and damage. In a 240 volts delta service, the corner grounded delta configuration involves one of the phase conductors being connected to ground. In this specific design, the ground fault interrupter system needs to be configured to monitor the current flowing through all three phase conductors, looking for any imbalance that indicates a ground fault. A ground fault in a delta system is different from a ground fault in a Y system. In a Y system, the neutral conductor provides a direct path for ground fault current to return to the source. In a delta system, there is no neutral conductor, so the ground fault current must return through other paths, such as through the grounding electrode system or through other equipment connected to the system. The ground fault interrupter protection in a delta system must be sensitive enough to detect these ground fault currents, even though they may be smaller than the ground fault currents in a Y system. Coordination of ground fault interrupter protection with other overcurrent protective devices, such as fuses and circuit breakers, is very important. The ground fault interrupter protection should be coordinated so that it trips before any other overcurrent protective devices operate. This ensures that the ground fault is cleared quickly and effectively, and that the risk of electrical shock and arc flash is minimized. The location of the ground fault interrupter sensor is also an important consideration. The ground fault interrupter sensor should be located as close as possible to the source of the power. This ensures that the ground fault interrupter protection system is able to detect ground faults anywhere in the system. The National Electrical Code provides detailed requirements for ground fault interrupter protection in various types of electrical systems. It is important to consult the National Electrical Code to ensure that the ground fault interrupter protection system is installed and configured correctly. The National Electrical Code Section 230.95 covers ground fault protection of equipment. This section requires ground fault protection of equipment for grounded Y electrical services of more than 150 volts to ground, but not exceeding 1000 volts face-to-face for each service disconnect rated 1000 amps or more. This requirement is intended to provide ground fault protection of equipment to reduce the likelihood of damage to equipment and fire. The maximum setting of the ground fault protection shall be 1200 amps and the maximum time delay shall be 1 second for ground fault currents equal to or greater than 3000 amps. It is important to understand that this is ground fault protection of equipment and not ground fault protection of personnel. Ground fault protection of personnel is typically provided by ground fault circuit interrupters, which trip at a much lower level, typically 5 milliamperes. Ground fault circuit interrupters are designed to protect people from electrical shock, while ground fault protection of equipment is designed to protect equipment from damage and fire. The National Electrical Code also provides requirements for ground fault protection of equipment for ungrounded systems. In ungrounded systems, ground fault detectors are typically used to detect the first ground fault. A ground fault detector is a device that senses the presence of a ground fault and provides an alarm or indication. The alarm or indication can be used to alert personnel to the presence of a ground fault so that it can be located and corrected. In ungrounded systems, it is not required to trip the circuit when a ground fault is detected. However, it is recommended that the ground fault be located and corrected as soon as possible to prevent the possibility of a second ground fault, which could result in a short circuit and a power outage. The selection of ground fault interrupter equipment should be based on the specific requirements of the electrical system. Factors to consider when selecting ground fault interrupter equipment include the voltage, current, and fault current levels of the system, as well as the type of grounding system used. It is important to select ground fault interrupter equipment that is properly rated for the system and that is compatible with the other equipment in the system. Installation of ground fault interrupter equipment should be performed by qualified personnel who are familiar with the National Electrical Code and with the manufacturer's instructions. It is important to follow the manufacturer's instructions carefully to ensure that the ground fault interrupter equipment is installed correctly and that it will function properly. Testing and maintenance of ground fault interrupter equipment should be performed regularly to ensure that it is functioning properly. The National Electrical Code requires that ground fault interrupters be tested monthly. Testing should include a visual inspection of the equipment, as well as a functional test to verify that the ground fault interrupter trips when a ground fault is simulated. Maintenance should include cleaning the equipment and tightening any loose connections. It is important to keep accurate records of all testing and maintenance performed on ground fault interrupter equipment. These records can be used to track the performance of the equipment and to identify any potential problems. In addition to the National Electrical Code requirements, there may be local codes or regulations that apply to ground fault interrupter protection. It is important to check with the local authorities to determine what requirements apply in a specific area. Understanding the different types of ground fault protection is essential. Ground fault circuit interrupters are designed to protect people from electrical shock. Ground fault protection of equipment is designed to protect equipment from damage and fire. Ground fault detectors are used in ungrounded systems to detect the first ground fault. Each type of ground fault protection has its own unique characteristics and is designed to address different hazards. Proper coordination of ground fault protection with other overcurrent protective devices is essential to ensure that the ground fault is cleared quickly and effectively. The location of the ground fault interrupter sensor is also an important consideration. The ground fault interrupter sensor should be located as close as possible to the source of the power. The National Electrical Code provides detailed requirements for ground fault interrupter protection in various types of electrical systems. It is important to consult the National Electrical Code to ensure that the ground fault interrupter protection system is installed and configured correctly. The selection of ground fault interrupter equipment should be based on the specific requirements of the electrical system. Installation of ground fault interrupter equipment should be performed by qualified personnel. Testing and maintenance of ground fault interrupter equipment should be performed regularly. It is important to keep accurate records of all testing and maintenance performed on ground fault interrupter equipment. In addition to the National Electrical Code requirements, there may be local codes or regulations that apply to ground fault interrupter protection. Consulting with a qualified electrical engineer or electrician is recommended to ensure that the ground fault interrupter protection system meets the requirements of the National Electrical Code and any other applicable codes or regulations. Furthermore, continuous monitoring of the ground fault interrupter system can provide valuable data on the health of the electrical system. This data can be used to identify potential problems before they cause a failure. Regular training for personnel on ground fault protection is also important. Personnel should be trained on the hazards of ground faults, the operation of ground fault interrupter equipment, and the procedures for responding to a ground fault. Ground fault protection is an essential part of any electrical safety program. By implementing a comprehensive ground fault protection program, organizations can reduce the risk of electrical shock, equipment damage, and fire. The calculation of available fault current is a critical step in determining the appropriate level of ground fault protection. The available fault current is the maximum current that could flow in a fault condition. This current is determined by the voltage of the system and the impedance of the circuit. The higher the voltage and the lower the impedance, the higher the available fault current. The available fault current must be calculated at each point in the electrical system where ground fault protection is required. This calculation should take into account the impedance of all conductors, transformers, and other equipment in the circuit. The available fault current is used to select the appropriate interrupting rating of the ground fault protection device. The interrupting rating is the maximum current so the device can safely interrupt. The interrupting rating must be greater than or equal to the available fault current. The grounding electrode system plays a crucial role in ground fault protection. The grounding electrode system provides a path for ground fault current to return to the source. The grounding electrode system must be properly installed and maintained to ensure that it can effectively carry ground fault current. The grounding electrode system typically consists of a ground rod, a ground plate, or a buried ground conductor. The grounding electrode system must be connected to the neutral conductor of the electrical system. The impedance of the grounding electrode system should be as low as possible to minimize the voltage rise during a ground fault. Surge protection devices can also help to protect against ground faults. Surge protection devices are designed to protect equipment from voltage surges caused by lightning, switching, and other events. Surge protection devices can also help to reduce the magnitude of ground fault currents. Surge protection devices should be installed at the service entrance and at any other location where equipment is susceptible to voltage surges. Arc flash studies are often performed to assess the hazards associated with arc flash events. An arc flash is a dangerous electrical explosion that can occur when a fault occurs in an electrical system. Arc flash studies can be used to determine the incident energy and the arc flash boundary. The incident energy is the amount of energy that a worker would be exposed to during an arc flash event. The arc flash boundary is the distance from the arc flash source at which a worker would be exposed to a hazardous level of energy. The results of an arc flash study can be used to select the appropriate personal protective equipment for workers who may be exposed to arc flash hazards. Regular inspections of the electrical system are essential to identify potential ground fault hazards. Inspections should include a visual inspection of all equipment, as well as testing of ground fault protection devices. Any identified hazards should be corrected immediately. A comprehensive safety program should include procedures for responding to ground fault events. These procedures should include steps for isolating the fault, energizing the equipment, and repairing the damage. Workers should be trained on these procedures so that they can respond quickly and safely to a ground fault event. It is important to consult with a qualified electrician to ensure that the GFI protected main breaker is installed and configured correctly.